Okay, guys. So, welcome to today's live stream on the Think Academy AMC books. So let me check the live stream settings. Make sure we can all see the screens properly. So, okay, sharing for a moment. Now we'll go back to sharing. Share screen. Okay. Okay. Okay, now I should be able to share the screen. Okay, so today we are going to continue our exploration of geometry problems. And today we are going to start off with an exit ticket problem. So let me get my pen ready. I will use color blue, okay? So the question says, circles of radius 2 and 3 are externally tangent and are circumscribed by a third circle, as shown in the picture. So let's find the area of the shaded region. So let's first use the given condition, that is, the radius of the circles are 2 and 3. Therefore, we can mark the other part of the radius, which is here in this part. That's also 3, right? Because radius is equal, and here it is 2. So in this case, we can find the diameter of the big circle, right? Diameter of big circle, that is 3 times 2 plus 2 times 2. Okay, so guys, are you able to see the share screen, or it's black? Okay, let me change the setting real quick. Okay, good. So now we should be able to see the share screen. Now we first find the diameter of the big circle, that is twice times 3 and 2 times 2, which is 6 plus 4. So the answer is 10. Okay, so that's for our first step. Find the diameter of the big circle. Then after that, we can find the area of the large circle, right? Since we know its diameter. So the area, which I'll use A to denote, of the large circle should be pi r squared, right? Now I will use capitalized R to represent the radius of the big circle. So that's pi times R is basically 10 divided by 2. And don't forget the square, okay? So that's pi times 5 squared, which gives us 25 pi, okay? So that's for the area of the big circle. Actually, let me add another step. So from the diameter, we know the radius of a big circle is 10 divided by 2, which is 5, okay? Now we are good with the first steps. Let me change the color to continue the second step. So we are asking to find the area of the shaded region. So it can be found by using the total area, exclude the area of the unshaded part, right? So I will first write area of the unshaded part, which is just the summation of the area of the two circles, right? So the first one is pi times the radius 3, so pi r squared now becomes pi times 3 squares, plus pi times this circle has a last radius, which is 2, so 2 squared gives 9 pi plus 4 pi, and the combined area of these two unshaded parts should be 13 pi, okay? Now we have the total area and area of unshaded part. Therefore, the area of shaded part is just their difference, so area of large circle minus area unshaded. That is 25 pi minus 13 pi, and the answer should therefore be 12 pi. So we are choosing option E, okay? So this is a very classic problem asking find the shaded region. So the general flow of thinking is always try to find the total area, exclude all the parts that are unshaded, then we should get the area of the shaded region. So that's for the exit ticket. Now we are going to another problem, which is a warm-up. So the problem says an isosceles triangle ABC is inscribed in a circle. So let's first mark the keywords here, which in this case is isosceles triangle. Okay, the two legs of a triangle are therefore equal. And we know this shape is inscribed in a circle with diameter AC. Okay, as shown in the below. So if AC is given to have a length of 10, it's asked what is the area of the shaded region. So first, let's find the area of the total figure, right? Then we can exclude the area of the unshaded part, which in this problem specifically is the area of the triangle. So I will write here the area of the circle is just pi r squares. So it's pi times, we know the diameter is 10, so it's AC divided by 2. Diameter divided by 2 gave us the radius. So that's pi times 10 divided by 2 is 5. So 5 squared, which is 25 pi. Okay, so that's the area of the total figure. Then next step, let's notice that since ABC is isosceles triangle, so for example, let's consider we make a height from B all the way, drop it down to the line AC. So here's our perpendicular side. Let's call this point D, okay? So in this case, since isosceles triangle, so D must be the midpoint of A and C, right? Actually, let me use a different color for better visualize purpose. So let me do a better color. I will do green. So, okay, suppose we are taking B as the point and the height is BD, where D falls on the line segment of AC, then we must know that BD is a radius, right? So BD is radius, and therefore it's half of the diameter, right? It's 1/2 times AC, which gave us 5, okay? Then we know the area of triangle ABC. It should be base times height, right? So what is a base? It's AC. And what is the height? It's BD, right? And never forget that divided by 2 at the end. So we should have AC to be 10 times BD. We have it to be 5. Then divided by 2. So that's basically 50 divided by 2. The answer should be 25, okay? Then it's our last step, which is find the difference between the total area and the unshaded part. I will start with area shaded is equals to area of the circle minus area. In this case, the unshaded part is just area of triangle ABC, right? So that should be 25 pi minus 25, okay? So among the answer A to E, which one gives the exact same result as we did? So that should be option A, right? I will also put a little box around our final answer. So in this question, we did the exact same technique as we just used in the previous one, okay? So I think after this page, there should be a quick information session, okay? I will zoom out a little bit. So before we move on to the next problem, here is a brief timeline for how to prepare for the upcoming 2025 AMCA. So first, as we are finishing up July, we will have our second round of real exam practice class, which actually starts today, okay? So this class is really beneficial for those who are preparing for the exam, because in this class, you will see real exam problems from past years, for example, 2011, 2013, 2018, and the most recent 2024. And after that, as we move to August and September, we will have our first round of AR and HR class. So AR class is designed specifically for those who are aiming to achieve the achievement role in the AMC exam. And HR class is about the same thing, but it will be a little bit more challenging since it's designed for those who are aiming to have the honor roll. And after that, we will have our second round of the AMC more test. It will be the exact same format as the real AMC exam, still 25 problem, all multiple choices, and the time limitation is 40 minutes, okay? So we will have another short-term modular class. So the modular class will be really helpful if your student is strong in, for example, 4 out of the 6 modulars covered in the exam, but needs some help or has some room of improvement for 1 or 2 modular, okay? So the result of this modular class, the focus of the class will be given shortly. And in October and November, we'll have another round of AR HR class, which is the same thing as the one in August, September, but we will include different problem sets for sure. another round of AMC mock test and modular class. As we step into December, we'll have our third round of AR and HR class, and of course, another round of AMC 8 mock test. Finally, before we head out to take the test in mid-January, we'll have our first short-term DHR class. So for DHR class, it's a class designed for those who are aiming for the distinguished honor roll. So the class will be focused on the last 3 to 5 problems from real problems in the past years. And we will have our last and final round of AMC mock test. So you can see there's a dozen of classes, 5 round mock tests. So if you're unsure about which class is right for you, you are very welcome to add me on my WeChat. So my WeChat ID is thinkvip60 with T capitalized, VIP capitalized, no space in between. And there's another very good resources we posted on Facebook. So it's a Facebook group. You can search on AMC8 helpful and educational math resources. So when you enter this group, there will be dozens of valuable resources for a student to work on, to get prepared. And we are also going to share some valuable problems. For example, the ones you see in the previous slides into that Facebook group, okay? So that's for the information session. Now we are ready for another real AMC problem, which is question number 18 from the 2020 AMC exam. So it says rectangle ABCD is inscribed in a semicircle with diameter FE. So let me get back to my pen. Okay, good. So now we have the rectangle ABCD is inscribed in a semicircle and the diameter is FE as shown in the figure. And of course, no figure shown, so we need to come up with a figure ourselves. The given condition is that AD, the length of the line segment AD is 16, and let's consider the length of FD equals AE is 9. What is the area of ABC? So for any geometry problem that doesn't give you a figure, let's try to draw the figure ourselves. We should start with the diameter, then we come up with a semicircle. Then, according to the instruction, we have our rectangle ABCD inscribed in the semicircle, okay? Let me draw it better. Okay, good. So let's mark all the vertices and the important points on our figure. I would say this is C, B, this is A, and this is point D, okay? So we are given that DF equals AE is 9. So let me also mark that on our figure. So that's 9 and also 9 here. And AD is 16. So let me use a different color. We know AD, the length of this part is 16. Okay. So what is our first step? So first step, let's try to connect C and O. But we do not have O here. So I'm assuming that O is the center of the circle. Okay. So it should be right here. Let's connect CO. Make this our first helping lines. Let me use a different color actually. So I will use orange, okay? So now CO is connected and we are going to find the area of triangle DOC, right? Because in this case, we can use the DOC by the Pythagoras theorem since we know the two sides of the triangle. Then we can find the length of the last side, which will be CD, the width of the rectangle. Then use the length times width, we'll get the area, okay? So that's the big picture. First step, I will write it down here. I will say connect CO, connect OC. Then as a result, we now forms a new triangle with the 3 vertex to be D, O, and C, okay? So in this case, let's notice that CO is a radius, OF is a radius. Why? Because FE is the diameter. So O is in the middle of F and E because that's the center of the semicircle. Okay. So OF is guaranteed to be the radius and as well as OE. Okay. So they are radius. Okay. So that should be enough for our first step. And what do we want to do on our next step is let's first find the total length of the line segment FE. So FE is composed of 3 parts. That's DF plus DA plus AE, okay? So we are given that DF and A is 9. So that's basically 9 plus 9. And what is the middle? It's the length of DA. It's also given to us, which is 16. So 9 plus 16 plus 9, we should get 18 plus 16. That's easily is 34. So again, FE is the diameter of the semicircle. So the radius should be the half of the length of FE. So we know in this case, the radius should be 34 divided by 2, which is 17. Okay, so 17 is our radius. So that's basically saying CO equals OF equals to OE is 17. So that's enough for our third step. And after that, we can have our, for our second step. And for the third step, first, let's write down what is the length of OD. OD is basically OF, the radius, minus FD, right, or DF. So OF, again, I mentioned that's the radius, so that's 17, and DF is given to us as 9. So the difference between these two line segments is 8. So OD is 8. Now, let's think about, let me write here for more space. So think about the Pythagoras theorem. Given that this is a right triangle, C, D, and O, okay? We now know OC, which is another radius, is 17, and OD, which is find its value to be 8. We can definitely solve for the line segment, for the length of the line segment CD, right? How to solve that? So first, let me write down the name of the mathematician, which is Pythagoras, and that's his theorem, okay? Pythagoras theorem. So basically CD square plus DO square should be equal to CO square. If you move around terms from the left-hand side to the right-hand side of the equation and also remove the power of 2, that's taking a square root of 2, we should get CD is equal to square root of CO square minus DO square, right? So let's plug in values. CO is the radius, so that's 17 squares, minus DO, which is find its value to be 8, so 8 square. And the difference, so what is the square of 17? That's 281. And what is the square of 8? So that's 64. And their difference should be 225, right? Okay, that should be 225. So you can actually check my answer. So the result, is 289 of the square of 17. So if you take a square root of 225, you should get 15. Okay, so 15 is the length for CD. Let me zoom out a little bit. Then how can we find the area of the desired rectangle ABCD? Base times height, right? Length times width. So that should be the easy step. I will keep using orange. So the area of our rectangle ABCD should be the width, which is CD, times the length, which is AD. That is 15 times, what is AD? We have AD given to us 16, okay? 15 times 16 should give 240. Okay, 240 is going to be our final answer, and A, B, C, D, E, which one to choose from? Gonna choose A, okay? 240. Again, so for the general technique to solve a problem like that, first, let's try to use the radius of the circle is always equal. Let's try to use this feature because usually we're going to use multiple radius of the circle. Then after knowing the radius, first we know the area of the circle, and then sometimes the radius can serve as the width or length of any inscribed rectangle or square, okay? After that, a very common thing to use here is the Pythagoras theorem. It's very powerful. It always helps us let know what is the side of a triangle given two of the sides known. So that's for this problem. And now we should be able to move to the exit ticket, okay? So it looks like the exit ticket is less challenging than the real AMC problem. The question says, a circle with radius 1 is inscribed in a square and circumscribed about another square as shown. It's asking for which fraction is closest to the radius of the circle. So first, let me still mark all the keywords here. Let me zoom in a little bit. Good. So I will use blue. We are given a radius of a circle is 1, and it is inscribed in a square and circumscribed about another square. So let's quickly go through what does the word inscribe and circumscribe means in this case. So inscribe and circumscribe both means the shape, they're just touching each other at one point. There's no gap, there's no overlap in between. So that's the exact meaning of the two words. And it's asking for which fraction is closest to the ratio of a circle's shaded area. and 2, the area between the two squares. Again, you can consider this question as finding the shaded area, okay? So what's our first step? Use the radius to get the areas of the circle. So, sorry, I zoom in too much. Okay, okay, wait. So, okay, now it should be good. Okay, good. So our first step, our circle number 1, that is the area of the circle, which is pi r square equals pi r square. So r is 1 in this case, the area is just pi, okay? Then we can also find the area of the small circle. Area of small square. How to find that? Again, we are going to employ the length of the radius. So let's consider this point O as the center of the circle. Then if we connect this vertex with O, we know the radius 1. Also here, this is 1, okay? And if you connect here too, you know it's also 1. Now, let's observe that the diameter of the circle actually is the diameter of the circle actually is the exact diagonal of the small square, right? So we all know that the area of the square can be defined as power 2, the square of its side length. However, there is another formula that can be used to find the area of the square. That is, take the square of its diagonal, then divide by 2. You can prove that yourself, but for time purpose, I'm just going to assume we all know that. So the diagonal, which I will write it all down, diagonal. Okay, so I spelled it. Then divide by 2. So in this case, clearly the diagonal is just 2. So 2 squared divided by 2 is 4 divided by 2. We know the area of the square is just 2. Okay, it looks like I stopped sharing. Let me continue to share it, okay? So I'm going to pause a little bit and share my screen one more time. Okay, so now you should be able to see my screen. Let's hold on for a few seconds for the YouTube to be able to reshare my screen again. Okay, good. So before we move on, I would like to briefly talk about where you can get all these problems. So these problems are derived directly from a book called the Think Academy AMC 8 book. So in this book, we not only include problems like this. For example, these are from the 100 tricky AMC problems. We also have problems that are separated into modulus, for example, geometry modulus, number theory modulus, and many, many more. And before each problem, there should be a given section called example, where you can see some example problems and get a big picture of what knowledge you are going to employ when you actually start doing a problem. And after that, we also have a detailed answer keys at the end of the book, so that when you finish your, for example, daily exercise, you can always refer back to the answer keys and check your own answers, okay? So can you see my screens now? Okay, so let me make sure YouTube is working. Okay, so let me see top chat. Okay, good. Now my screen is back up. Now we can continue from the part where I left. So now we are talking about how to find the area of the small square. That is diagonal square divided by 2. So that's 4 divided by 2, which is 2. Then next step is find the area of the most outer circle, outer square, right? The largest square. So I will write the area of large square. In this case, clearly the diameter of the circle is just its side length. So simple application of the formula is 2 squared, right? So that should give you 4. Now that's enough for our first step. I will go to step number 2 using a different color. Okay, good. So now let's just find the difference between the areas of the squares and also the circle, okay? So I will write it as areas circle shaded. Circles shaded area. In this part is a difference between the area of the circle. So that's area circle minus the area of the small square. Okay, so let's just plug in numbers. And the circle is pi. Area of the small square is 2. So in this case, since we are not looking for the exact solution, just the approximate answer, let's take pi as 3, okay? So that will be really convenient for the following calculation. Then 3 minus 2, we have the result to be 1. Then we are not done yet. We are also going to find the area between the two squares. Areas between squares. So that's just 4 minus 2, right? Area of a large square minus area of a small square. So that's 2. Therefore, our desired ratio is 1 for the numerator and 2 for the denominator, right? So I'll put a little box. In this case, we are choosing option A. So again, for this problem, it really tests on if you know there's an alternative formula to calculate the area of a square. So if you know that, you can just apply diagonal square divided by 2. If you do not know that, then you to apply the Pythagoras theorem and calculate the length of the leg of the triangle, then redo the entire thing using the basic formula, right? So in this case, that will take a little bit longer time, but both methods works out. So again, before we move on to our fifth problem of today's live stream session, let me quickly give you introduction to our timeline for how to prepare for the upcoming 2025 AMC. As we are finishing up July, this is the first day of our second round of real exam practice problem session. So in this class, you are going to be offered 6 different problem sets that are derived from, that are exactly the real problem from the previous year's AMC exam. For example, in the second round, we covered the year of 2008, 2013, 2018, and the most recent 2024. Again, if you are preparing for the upcoming AMC8, this class is the one that you are highly recommended to take, because that's not going to offer you a good sense of what kind of problem, what style of problem you are likely to encounter in the real exam. Also, it will help you practice your time management skills while taking the actual exam. So as we step into August and September, we will have our first round of AR and HR classes. So AR class is designed specifically for those who are aiming to achieve the achievement roll in the AMC, and HR class is designed for those who are shooting for the honor roll. Okay, so HR class will have the exact format as AR class, but a little bit more challenging, as the focus of the class will shift a little bit to the later part of the problem. So that's for the AR/HR, and we have our modular class, our mock test. So modular class will be decided which modular to use recently, and that will be helpful if, for example, you are very strong in 4 out of the 6 modulars, but do need some assistance or have some room for improvement in 1 of the 2 modula. Okay, so that will help you a lot by taking the class. And as we enter the August and November, same thing as AR/HR, same thing as modular, but a different modular will be covered. And our third round of the AMC8 mock test, almost the same thing in December. We have the mock test, the third round of AR/HR, and as we ready to go to the test in mid-January, before that, we will offer you a short-term DHR class. So that's for students who are aiming for the distinguished honor roll. So in this class, the main focus will be about the last 3 to 5 problems, and there will be our final round of AMCA mock test. So there are a lot of classes and a lot of exams. If you are not sure about which one is right for you, you are highly recommended or very welcome to add me on WeChat. So my WeChat ID is thinkvip60 with T capitalized, VIP capitalized, no space in between. And there's also a good resources you can find on the internet. That's called Facebook group AMC8 Helpful and Educational Math Resources. So if you search on that if you search that on Facebook and you enter the group, you will see we are offering a lot of problems you can study for. Get prepared for the exam. Also, we are going to share some experiences of text taking. Okay, so that's for this information session. Now we are ready to see another problem from the geometry module. So the question is asking for how many rectangles are there in this figure. So let's count it. Okay. First, let's count the most basic rectangles. So the one that you can directly see it by taking the first view of this figure. I will just write basic. So first, there's 1, right? This is our second rectangle. This is our third, and this is our fourth and the fifth. So basic, we have 5, right? So that's not hard for this part. Then we can count the ones that kind of is the overlap part of the 2 basic rectangle. So I will say they are formed by overlapping. So I will change a different color for better visual purpose. So the first one is here. That is the overlap part created by the first and the second basic rectangle. And this is our second one, the third one, okay? So we can write it as 3. And finally, think about the rectangles that are formed by more than one, right? So we already have the 3 overlaps. And so the only one left should be, let me use a different color. Let's use orange. Should be this one, right? So this rectangle, if you look at closely, it actually is formed by 2 of the basic and 2 of the overlap. So I will say this is all these rectangles together. You get 5 plus 3 plus 1, which is 9, okay? So that's why I choose option D. And similarly, let's see a more challenging problem. Okay, looks like the screen sharing is done again. So how about let me stop sharing and resharing it one more time. So let me create a share screen. So I will share my live screen. Okay, now we should be able to hold on for a few seconds before the screen is up again. Okay, so welcome for those who just entered the live stream session. As I just talked about, for all those problems I just covered, it's all derived from our Think Academy AMC book. So in this book, we not only included 100 tricky AMC problems, but also these problems are separated into modules. In this case, you can always turn a look of the content and go to the exact session that you're interested in. For example, you want to focus on geometry session in the next few weeks, then you can turn on the page to a geometry section. First, you can go through all the key formulas and key information about like area, the surface area, and maybe the volume. Then after you are familiar with all those, you can view 1 or 2 exam problems before you actually start doing any exercise. So the purpose of that is you can always check what the part you are missing before you do the homework. And also beside that, we have a detailed answer keys attached at the end of this Think Academy book. In this case, when you finish doing a problem, you can always refer back to the answer keys and check your own answers. So in this case, you can do practice whenever you want, wherever you go, okay? So how to get this book? There are 2 major ways to get this book. First, if you are an existing customer of Think Academy, especially your children is going to be in the incoming grade 4 and grade 5, then this book should be a hard copy of this book should be sent directly to you. If you haven't got a book yet, you're welcome to add me on WeChat. I will post my WeChat ID on the exact next slide. And if you are a new customer who haven't enrolled in Think Academy before, you have the opportunity to book a $1 trial class. When you finish the class, we will also send this book to you as a bonus, okay? So that's for the 2 ways of getting the book. So for both existing and new students, you're very welcome to add me on my WeChat. So let's see if the screen sharing is up. So let me refresh the page again. Okay, looks like I'm going to have, okay, now it's up, good. So sometimes, I don't know, it's due to the YouTube or my own issue, the screen share is down for a few seconds. Thank you for the tolerance. Now it's a real AMC problem. It's asking for the exact same desire as the last one. It's asking for how many rectangles are in these figures. So let's circle the keywords. Okay, zoom out too much. So let me zoom in a little bit. Okay. Okay, good. So now we are looking for the total area of rectangles. So let me get my pen ready. Okay, so how many rectangles are in this figure? In this one, we can definitely do the exact same technique we did in the previous problem, but now it has definitely more triangles. And in order to avoid getting lost, let's try to think about first counting the triangle that are composed by only one section. Then think about those are composed of 2 sections, then similarly composed by 3 sections, and so on, okay? So let's first do 1 section, rectangles, 1 section. Clearly, there are just 3. What are the 3? So this is our first one. You see, in this rectangle, we have no other section, just 1 section. So that's why I call it 1 section rectangle. This is our second one. This is our third one, right? So that's very straightforward. We have 3 triangles for 1 section. And for the 2 sections, okay? For the two sections, we should have 5. Which are the 5? So I shifted too much. So let me get my pen in a different color. How about orange? So in this case, this is our first one, composed of more than one section. This is our second one. And this is the third two-section triangle. And this is the fifth. Okay, this is the fourth. So, and we should have another one, right? So where's another one? Is this one, right? So we should have 5 two-section triangles. In this case, let's put the answer 5 for the two-section. And how about any triangle is formed by 3 sections, okay? So what are the 3-section triangle? 3 sections. Okay, so for the 3-section triangle, can you observe any of the 3 sections in our figure? No, right? So there should be no 3-section triangles. Actually, let me write it better. Okay, so for the 3 sections, we have 0. Now we can move to rectangles that are formed by 4 different sections. Okay, so what are the 4-section rectangle? I will use green to mark the boundary of these kind of rectangles. The first one, it should be this one, right? This top one. Because as you can see, we have 1, 2, 3, and this is our 4th section. And also, 4-section triangle should also be this one as well, right? We have this our first section, second, third, fourth section. And this very long triangle is also composed of 4 different sections. So that's 1, 2, 3, 4. In this case, how many 4-section triangle rectangles do we have? We have 3, okay? There are 3 of this type. And do we have any rectangles that are formed by more than 4? No. The largest number of sections that can be put into one triangle in this problem is 4, right? You can check yourself, but you should get 0. So if we add up all these different cases, we have 3 plus 5 plus 0 for the third type and plus 3. So that's 8 plus 3, which is 11. We are choosing option D, okay? So a quick review of how to do the problem. In order to avoid getting lost in counting, we can always separate all those triangles into groups, right? Classify them into groups based on the number of sections contained inside. So that's for this AMC 8. It's problem number 19 in the 2011 AMC exam. So welcome again for those who just entered the live stream session. In this session, we're going to cover about problems, and also there is a quick review of what is the timeline for our upcoming 2025 AMC 8. First, as we finish up July, today is actually the first day of class for the real exam practice class. In this class, the instructor will cover detailed explanation about real problems from the past year's exam. For example, in the second round, we will talk about exam problems from 2011, 2013, 2019, and also the most recent 2024. After that, as we step into August and September, we will have our first round of AR, which is a class designed specifically for achievement roll students who are aiming for that prize, and also for those who are aiming for the honor roll prize. So besides that, 2 classes, we'll have our first round of AMC mock test and our modular class. So the modular class will be really beneficial for those who are very strong in maybe 4 out of the 6 modular covered in the test, but need some assistance or have some room for improvement of the rest 1 or 2 modular. Okay, so the exact modular which will be covered will be determined shortly. And in October and November, we will have our second round of AR/HR class, another modular class which is different from the previous one in August, and another round of AMCA mock test. So almost the same thing in December, but while we are ready to go for the exam in mid-January, we are going to offer you a DHR class. So that's for Distinguished Honor Roll, for those who are aiming for that prize. So this class will be focused more on the last 3 to 5 problems, and we'll have our final round of AMCA mock test. So for those of you who are not sure among all these classes, which one is the best to take, you are very welcome to add me on WeChat. So my WeChat ID is ThinkVIP60, capital T, capital VIP, no space in between. And for those of you who are using Facebook, there's a Facebook group called AMC8 Helpful and Educational Math resources. So if you search these keywords on the searching pack, you are going to see the group, and when you enter, we're going to share you all those valuable problems you can use to prepare for the exam, and there will be a lot of exchange of information and experiences for test taking skills. Okay, so I will pause here for maybe 10 more seconds. You can take a screenshot, take a picture, or copy down my WeChat ID and search keywords for the Facebook group. Okay, so we have 2 more problems left for today's session. So the second from the last is again an exit ticket problem about counting the number of rectangles. Okay, so these are the keywords, and let's try to use the same technique as we just did. So we are classify all these rectangles based on the number of sections they have. So first, we have our one section rectangle, and how many of them? So that's 1. This is 2. This is 3, 4, 5, and 6. Okay, just 6. Oh, sorry, I zoom out too much. So let me zoom it back in. So we should have 6 of these kind of rectangles. Okay, so that's 6. Still zoom out too much. Okay, good. Now I should be fine. So we have 6 of them. How about rectangles that are composed of 2 sections? Okay. So if you consider about these kind of rectangles, we should have, let me clear up the graph a little bit. Okay, good. So, okay, let me get back to my pen. So for the 2 section rectangles, this is our first one, this is our second one, this is our third one, and fourth one. So are we done with all these 4? No, we have a few more, right? So this is also a 2 section rectangle, and also this one, and the last 2 should be these 2 top ones. Okay, so these are how many? 4 plus 4, which is 8 2 section rectangle. So think about the number of 3 sections rectangles. How many numbers do we have? Nothing, right? We does not observe any rectangle that is formed by 3 sections. So 0 should be our answer for this type. And how about 4 sections rectangles? So 4 sections, there should be a few more. So let me use a different color, for example, green. So in this case, as I mark the boundary of this green rectangle, we can see there's 1, 2, 3, 4 part. Here also, there's another one. It's about symmetry, right? And also in the middle part, there's another one. So are we done with all the 4 sections? I don't think so, right? We also have those that are kind of displayed horizontally. This is another one, and this is another one. Okay, so in total, how many 4 sections rectangle do we have here? We have 5, right? So 2 vertical, 2 horizontal, 1 in the right middle. So let's go back to blue for the answer. 4 section is 5. How about 5 sections? Triangles are rectangles that are composed of 5 different sections. So what are these? So there should be only 2. Which 2? So let me use another color. How about red? Okay. So if you see here, I use red to mark the boundary of this rectangle. Here's 1, here's 2, 3, 4, 5. So that's 5 sections, right? And there's another one due to symmetry right beneath it. So that's also a rectangle formed by 5 different sections. So that's 1, 2, 3, 4, and here's our 5th section. So 5 section rectangle, we have 2 of them, and we continue for the 6th section rectangles, which doesn't exist. Okay, there's no 6 section rectangles and no 7 sections rectangles. You can count yourself, but I'm pretty sure you will not find any of these type of rectangles. And now how about 8 section? Okay, 8 sections rectangle. This should be really easy to observe because let's use symmetry. Okay, so the one rectangle in the middle, sorry, let me draw it better. So this one, I use black to mark the boundary. Clearly, it's the only one that is composed of 8 sections. So it's 1, 2, 3, 4, 1, 2, 3, 4. So 4 plus 4, we have 8 sections, and there's only one rectangle of this type. So we put 1 here. How about 9 sections? Are there any rectangles that are formed by 9 sections? There's two of them. So which two? Let's think about just adding one more section to our existed 8-section rectangle. So I'm kind of run out of colors. I will use purple. So think about this rectangle, okay? This purple rectangle. I will mark the boundary seeker so you can better see it on my figure. Okay, as you can see, the purple rectangle has 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9 sections. And since we have the top one, the bottom one must be the exact same case due to symmetry, right? So again, in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, and this is our 9 section. So in this case, we have a pair of 9 section rectangle. And finally, do we have any 10 section rectangles in this figure? I use a different color. So let me get back to blue. 10 sections. There should be one, only one. What is the one? It's the entire figure, right? So that's 8 in the middle, 1 on top, 1 on bottom. So 8 plus 2 gives you 10, right? Never forget the entire figure. It also counts, okay? So now our task is to add up all the numbers for different types. So we have 6. So I will say add up. By adding up, we have 6 plus 8 plus 0, so we do not write it, plus 5 plus 2 plus double 0, so that's still 0, plus 1 plus 2 plus 1, so that's 14, plus 5 is 19, plus 2 is 21, 21 plus 1, 22, 22 plus 2 plus 1 is 22, add 3. So the answer should be 25. So which option is the same as the result? That's option D, okay? So again, let's do a quick review of a problem like this. You see there are 25 triangles in this picture. So it's really important that you keep track and keep the classification of your rectangles consistent. Otherwise, you may lose in the middle and do not know which one is counted and which one is not. So one of the good way is to classify all these rectangles by the number of sections they have. So that's for this problem. And for the last one, okay, the last one is a really interesting geometry problem. It says there are 64 small cubes. So let me highlight the keywords. Okay, blue. So there are 64 small cubes with an edge length of 1. This is good because we know the area of each face, which is 1 square, should be 1, right? And which among these 64, 34 are black and 30 are white. Now, we are arranging the 64 small cubes into a 4x4x4 large cube. As shown in the figure below, what is the maximum area of black part on the surface of the large cube? So think about if we want to achieve the highest number of black faces on our large cube, which are the most ideal position to arrange these black cubes? On the corner, right? Why? Because if we put a little cube on a corner, you have exactly 3 faces facing outside. So that will be counted as 3 faces, right? And that is the maximum number of faces you can have in this cube. Think about if you put the little cube of black in the middle, only 1 face is going to be seen from outside. So that only counted as 1 face. And if you put instead of on the corners, you put it on the edges, then you will have just 2 faces, right? That's not optimal enough. We want to have as many faces facing out, so that will be counted. In this case, the best position to put these black cubes is the corners. So quick question, on the large cube, how many corners do we have? We should have 8, right? So again, on a cube, we have 8 corners. So our first and most desired position to put those black squares is on corners. I would say put on corners first. So that will be 8. Then for each corner cube, we have 3 faces facing out. So that should give us 24 faces in total for those corners black cubes. Okay. Then as I just said, the second best position to put these cubes without putting them on the corners is on the edges. Okay. So I would say put on edges. Put on edges. Why on edges? Because although we only have 2 faces facing out, that's still good. Then it's still better than put them in the middle because that will be only 1 face. So for example, these two cubes are put on the edges, and let's count the number of faces facing outside. So that's 1 is 2, right? So that we count it as 2 faces. And how many kind of these edges do we have on this big cube? We have 24 of them, right? We can count it. So that's 2, that's 3, 4, 5, 6, 7, 8, 9, 10. On the other side, 11, 12. On the other side of this 2 is 2 more, and here, and that should gives you add up 24, right? So among these 24 faces facing out, among these 24 small cubes of black, each of them has 2 faces facing out, right? So in total, the number of faces facing outside is 48. Okay, so our last step is, now we have how many cubes already used? 8 plus 24 is 32. So how many cubes do we left? It's the difference between the total, which is 34, and the number of cubes we just used, right? So these, there's no other way to put them. We have to put them in the middle. So these will be 34 minus 8, which is come from here, and minus 24 come from our second step. So that will be 34 minus 32, which gives us 2. Then each of them only have 1 face facing outside, right? So times 1, you get 2. So let me add a little notation here. So the first step is for 3 faces. So that's for 3. The second step is for 2 faces facing outside. And here, 1 is just for 1 face. Okay, now our final step is to add up all the numbers. Which numbers? The number of faces, right? Because each face has an area of 1. So in total, there should be, let me finish it up using using green. So the total number of faces is just the ones on the corner is 24, plus those are displayed in the edges, that's 48, and plus our last 2, okay? So that's 50 plus 24. If you add up the last 2 numbers first, you should get 74. Okay, so that's why you're choosing option D. Again, when you're asking for a problem like what is the maximum, what is the minimum area of the surface area of a solid figure, always try to think about where are the position that kind of has the most number of areas facing outside. So if you're concerned about the most area, try to put your object on those faces, on those positions. For example, in this case, it's the corners. Then when the corners are all used up, let's go to our second best positions. When the second best position is filled up, we go to our third best. So that's the strategy, okay? So, and of course, if you are given a question asking for what is the minimum area, try to avoid those corners and edges. Then you have less faces showing up, which will give you the minimum area as desired. Okay, so I think that's all for today's live stream. Again, really appreciate you guys for coming. And I think I will upload the playback of this video shortly after I finish. And also the notes and the original problem without any notes will be uploaded on our WeChat group using the Google Drive link I provided. All right, thank you again for coming, and I wish you have a good rest of your days. I will see you guys. Bye.